Okay, another big integration technique called trig substitution. And before we get started, our substitutions are going to involve taking advantage of these three identities. So you'd want to know these. And all three of them can be thought of as coming from the most important trig identity that you should definitely know, which is sine squared theta plus cosine squared theta equals 1. If I subtract the sine squared over, I get 1 minus sine squared theta equals cosine squared theta. If I take sine squared theta plus cosine squared theta equals 1 and divide everybody by cosine squared, I get tangent squared theta plus 1 equals secant squared theta. That's another identity. And if I just subtract 1 from secant squared, I get secant squared theta minus 1 equals tangent squared. These three identities are the only three really, well, these are the big three that we're going to use for our substitutions. You do need to be familiar with other identities, but those are the ones we're going to base this idea of trig substitution on. Okay, let's start with this integral, the integral from 0 to 2, the square root of 4 minus x squared. And I want to start with this because this integral came up earlier, it probably came up earlier in this course. And what we would have told you to do on this one is use geometry, because u substitution will not work. If I let u equal the inside, du would be negative 2x, and I don't have that anywhere to accommodate the du term. But then we learned early on we can think of this particular function as the top half of a circle of radius 2. And if my integral goes from 0 to 2, that means I want the area under this circle from 0 to 2. This is just 1/4 of the overall circle. So I can just use the formula for the area of a circle, 1/4 pi times r squared. That gives me pi. And that's really not too bad. That's pretty simple as long as you recognize that as a circle. Now, we can do the same integral using trig substitution. So here's what we would do. It's kind of like u substitution, but instead of letting all of this be u, we're actually going to replace this x. Okay, here I'm talking about why u sub doesn't work. So let's go to the next page here. We're going to let x be 2 sine theta. So we're substituting x equals something rather than the whole thing equals u. Now, why are we making that a choice? So let's think ahead here, okay? What we're trying to do, if x is 2 sine theta, and I put it in here, that's going to turn into 4 minus 4 times sine squared theta. And after I take out the 4, I left with 1 minus sine squared theta, which I could replace with cosine squared theta. So the motivation for letting x be 2 sine theta is so that I can eventually get a 1 minus sine squared theta that it can be replaced with cosine squared theta, okay? There are rules. Some teachers in the book will try to teach you rules for how to choose your x. I'm not good at memorizing rules. So instead, I want you to think about why we're doing that, okay? And we'll see some other examples and you'll kind of learn why we choose x to be what it is. Okay, it is a substitution. So if we let x be 2 sine theta, we want to change the whole integral in terms of theta. So I have to do the derivative of both sides to generate a d theta. dx is going to be 2 cosine of theta times d theta. And here I'm not trying to match it up like when we do u substitution. I literally am just going to replace that dx with 2 cosine theta d theta, because now my integral is all in terms of theta. Okay, we talked about this. So remember, this 4 can come out as a 2. This 2 cosine theta is going to come out, so we'll have a 4 outside. On a previous video, we talked about the dangers of just saying the square root of something squared is just the something. So let's talk about that. Before we make the square root of cosine squared cosine, we need to make sure that whatever is inside here is positive. So if we convert these limits in terms of theta, my upper limit was 2. Remember, x was 2 sine theta. So if I put that in to this substitution, that's the equivalent of saying sine of theta is equal to 1, which means theta would be pi over 2. And if x was 0, which was my original lower limit, that would be the equivalent of theta being 0. So my limits in terms of theta are from 0 to pi over 2, where we know cosine's positive, right? Cosine's positive, in which case the square root of cosine squared is just regular cosine theta. I don't have to worry about a negative there. And that'll get me to 4 cosine squared theta. And for cosine squared theta, remember we have to use the half angle identity, 1/2 times 1 plus cosine of 2 theta. Pull out the 1/2. The integral of 1 with respect to theta is theta. Cosine of 2 theta integrates to 1/2 sine of 2 theta. Since I already converted my limits in terms of theta, we'll just plug in from pi over 2 to 0. And when I work that all out, I get the same answer as it should be. We got using geometry, which is pi, which then brings up the question, of course, this was a full page of work. If you can see it using geometry as just the top half of the circle, and then specifically just the top quarter here, obviously that's going to be much faster, and you would definitely want to do that. So here's another one. So how do you know when to use trig substitution? Well, you definitely would want to try u sub first. But here, I mean, if you kind of play around with it, if you let u equal 49 minus x squared, you don't have the negative 2x or even an x to accommodate the du. Oftentimes you'll notice there are integrals that are something minus x squared, or x squared plus something, or x squared minus something. They usually have an x squared in there. Now in this case, I'm still thinking, trying to get my 1 minus sine squared. What would I want to let x be for that to happen? Well, if I've already got a 49 sitting there, I want this to turn into 49 sine squared theta, so that I could factor out a 49 and be left with 1 minus sine squared. So that's my logic in letting x be 7 sine theta. Because then when I square it, it's going to be a 49, which I can pull out. Of course, dx is the derivative 7 cosine theta d theta. So the dx gets replaced with that. This x gets replaced with 7 sine theta, and we plugged it in there as well. Okay. The 49 under the square root comes out as a 7 in the denominator. 1 minus sine squared is cosine squared. Now, unlike the last problem where we had limits and we had to make a decision whether this was positive or negative before we simplified it, we don't have any limits of integration. So we're gonna think positively, pun intended there. We're gonna assume that cosine is positive. So we'll just say the square root of cosine squared is cosine. We can cancel those out. Leaves me with cosecant theta. And if you recall, the integral of cosecant of theta is natural log of cosecant of theta minus cotangent of theta plus a constant. Now, we started this integral in terms of x, so we should finish it in terms of x. We're not done yet. To get this back in terms of x, if you go back to your original substitution, x equals 7 sine theta, that says the same thing as sine of theta is equal to x over 7. If you draw a triangle then that represents that, a right triangle, sine of theta is opposite over hypotenuse, x over 7. Do a Pythagorean theorem and you'll get this other side to be the square root of 49 minus x squared. Now we can refer to this triangle. Cosecant of theta is the reciprocal of sine, so instead of x over 7, it will be 7 over x. That's what that turned in there. Cotangent is the reciprocal of tangent, so instead of opposite over adjacent, it will be adjacent over opposite. That's this term here. And they do have the same denominator, so you can make that one fraction here. and I get my final answer. Lots of examples here. Here's the next one. Dx over x squared times the square root of x squared plus 4. Now you're thinking, okay, remember the three identities? We just did two in a row where we were trying to use 1 minus sine squared. Well, this looks nothing like 1 minus something squared or a number minus something squared. So the identity that most resembles something squared plus a number is tangent squared theta plus 1. Because remember, that equals secant squared theta. So we're going to try to take advantage of this identity, which means what would be a good choice for x? Knowing that I have a 4 there, I'm going to let x be 2 tangent theta. Hopefully you're starting to pick up on this. Why 2? Because if I square that, it's going to turn into a 4, which I could then factor out the 4 between these two terms and take advantage of my identity, which would be secant squared. Okay, remember to put your dx in, and your x is 2 tan theta as well here. After I simplify that and square it, that's a 4. Cancels this out with a 2. This 4 will come out as a 2. Okay. I feel like there might be a mistake here because this will come out as a 2, but 2 over this left wing with a 2, so I think this should be 1/4. Because there was still a 2 here next to this tangent squared theta. Okay. Apologize for that. All right, so we'll assume secant squared, secant is positive, squared is secant, squared is secant. That will cancel with 1 power of secant on the top, leaving me with secant over tangent squared. So 1/4. Okay. If you get stuck on secants and tangents, especially if they're divided, maybe change everybody to sines and cosines is a good strategy. So secant is 1 over cosine. Tan squared is sine squared over cosine squared. Should be 1/4. If you flip and multiply, you'll be left with cosine over sine squared, which now works out nicely with a u substitution. Let u equal sine, du is cosine theta d theta, which is the numerator. So this is just 1 over u squared du. Thinking of 1 over u squared as u to the -2, that integrates to u to the -1 over -1, which is -1 over u. So this would be -1/4, well, -1 over 4 sine theta, which is -1/4 cosecant theta. And remember, to get this back in terms of x, we go back to our original substitution. If x equals 2 tan theta, then tan theta is equal to x over 2. So draw a triangle, opposite over adjacent, x over 2. Pythagorean theorem gives me the square root of x squared plus 4 is the hypotenuse. Cosecant is the reciprocal of sine. So instead of opposite over hypotenuse, it's going to be hypotenuse over opposite, right there, plus c. More here. All right. So you see a lot of these have square roots, right? That's not all of them, but many of them do have square roots. That's how you, and if u sub doesn't work, that's how you know to use this. Now this time, this one's a little different. Our 3 identities, let me go back to our 3 identities, okay? We have 1 minus sine squared theta, tan squared plus 1, secant squared minus 1. So the way to think of this is if you get an integral that has 1 minus, or a number minus something squared, you're going to probably use this one. If you have something squared plus a number, you're going to use this one. And if you have something squared minus a number, you're going to use this one. When I look at this, I see something squared minus a number, right? So this is one I want to use. I want to try to make this look like secant squared theta minus 1. Same rationale though. I want to let x be 2 secant theta because I know I'm anticipating I'm going to square it. And that's going to become a 4, which I can then factor out. Okay. Dx is 2 secant theta tangent theta. That's up here, d theta. And I put my x's in for both of those. Let's see if I simplified this correctly this time. 2 to the 4th is 16 secant to the 4th. The 2 and the 16 reduces, I'll have an 8 in the denominator. The 4 that I take out here is going to join that and become 1/16. Good. One of my secants cancels here. So I'll have secant cubed. Secant squared minus 1 is tangent squared. Square root of that is tangent of theta, which cancels out the tangent in the numerator. And I'm left with 1/16. It's really 1/secant cubed, but 1/secant cubed is the same as cosine cubed. Where is it? There we are. That's the same as cosine cubed. 1/secant cubed. And that was actually, I think that was one of the examples we talked about when we did powers of trig functions. You're going to break this up as cosine squared theta times cosine theta. This is going to become my du, and I'll change cosine squared theta into 1 minus sine squared theta. Do your u substitution. Get down to this and use our original substitution. I like to do this at the end. You can do it at the beginning if you want, but once I know I have to get this back in terms of x, I can always go back and draw my triangle. The secant of theta should have been x/2. Instead, hypotenuse over adjacent, right here. Pythagorean theorem gives you the square root of x squared minus 4. And so then the sine of theta is opposite over hypotenuse. And then I also have sine cubed, so it's this over this cubed. When you cube the square root, you can think of that as to the 3/2 power. And then the bottom is just going to be x cubed. As you can see, oh, here we go. It's kind of a summary here. Kind of just a summary of those 3 trig identities. And kind of what I'm saying, if you see something squared minus x squared, you're going to want to let x be a sine theta. X squared plus a squared, x will be a tan theta. X squared minus a squared, x will be a secant theta. So if you want more specific substitutions. As you can see though, this is a long process. And it's very common for students to use trig substitution when they didn't even really have to. Okay, and you know, especially on a test where time is of importance, you don't want to waste time on a problem when you could have done it in an easier way. So make sure you've seen I've at least considered u substitution before trying trig substitution. This one looks an awful lot like one of the ones we just did, and what I will tell you is you can solve this with trig substitution. It will work, but it's going to probably take you twice as long to finish it. So notice here, if I let u equal x squared plus 16, du is 2x dx. I can wish for my 2, compensate with a 1/2, and it's a pretty straightforward u substitution. Even times, also remember that, you know, there's times when you think u substitution isn't going to work out, but it can work out. Here, if I let u equal 4 minus x squared, du is negative 2x dx, I can steal an x from the x cubed in the top. That'll leave me with x squared here. I can wish for a negative 2 and compensate with a negative 1/2 to get my du. Remember this idea, if you have leftover x's, sometimes you can go back to your original u choice and notice I have an x squared there. If I solve for x squared, it's equal to 4 minus u. So I can replace that leftover x squared with 4 minus u. Bottom was u to the 1/2. There's my negative 1/2, which can be pulled out. And remember, if you have a fraction with one term in the bottom, best way to go is to split it up into two fractions. 4u to the negative 1/2. If you reduce u to the first over u to the 1/2, that's just u to the 1/2. Do your power rule, plug back in your x. So notice these last two examples did not require trig substitution. Make sure you've checked everything before you go resorting to trig substitution. Okay, one more here. Now, if it's x squared over the square root of 4 minus x squared, u sub isn't going to work. You could steal an x. If you let u equal 4 minus x squared, du is negative 2x dx. You could steal an x to satisfy the du, but that would leave you with a leftover x, which we'd kind of get stuck with. So now we're going to go back to trig substitution. Think about your correct choice for x. And if, in fact, at this point, maybe a good idea to pause the video and make sure you can work it out without just copying here. And then come back and let's check through this. So here you'd want to let x be 2 sine theta. Dx is 2 cosine theta. So there's x squared right here. There's dx. 4 minus 2 sine theta squared. All right, this is 4 sine squared theta times 2 cosine theta. Here I know that's 4 minus 4 sine squared, so I'm already factoring out the 4. That will come out as a 2. Square root of cosine squared, which is what you get when you use your identity, is just cosine. That cancels this out, leaving us with sine squared theta, the integral of sine squared theta, d theta. Use your half angle identity. I brought out the 1/2 with the 4, that became 2. Antiderivative of 1 with respect to theta is theta minus 1/2 sine of 2 theta. Now, the reason I wanted to show you this one as our last example is, how do we get this back in terms of x? We've been using our triangle. I can slide this down a little bit more. We've been using our triangle, but our triangle only tells things about sine of theta or cosine of theta. But here this is sine of 2 theta, right? So what do we do with that? Well, there is a double angle identity many of you have probably seen. We need to use this. The sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. So if I replace that, 1/2 and the 2 cancel out. Now I can go back and, because everybody's just in terms of 1 theta, I can use my triangle. If you just have a theta left, you can use technically any 6 of the inverse trig functions to express theta. The standard thing, though, is to use your original trig function. Remember, our original substitution was x equals 2 sine theta. So the standard thing is to use inverse sine in this case. Theta is the angle whose sine is x over 2. And then for sine of theta, opposite over hypotenuse, cosine of theta, adjacent over hypotenuse. And I think I distributed the 2 to get this answer here. All right, lots of practice. As you can see, this takes some practice to get good at it. So pick some problems from the book, keep practicing them.